Chapter 13, Elements as Money. If the periodic table has a history with politics, then it has an even longer and even closer relationship with money. The stories of many metallic elements cannot be told without getting tangled up in the history of money, which also means getting tangled up in the history of counterfeiting, the faking of money. In different centuries, cattle, spices, porpoise teeth, salt, cocoa beans, cigarettes, beetle legs, and tulips have all been used as money, none of which can be faked convincingly or easily. It's tough to make a fake cow. Metals are much easier to counterfeit. Transition metals are especially easy since they have similar chemistries and densities because they have similar electron structures, and they can blend together and replace one another in mixtures of metals known as alloys. Midas's zinc touch. Around 700 BC, a prince named Midas inherited the kingdom of Phrygia in what is now Turkey. Midas sometimes receives credit for discovering tin, not true, though it was mined in his kingdom, and for discovering some other minerals, but no one would remember Midas today if not for his infamous gold touch. He earned it after helping the minor Greek god Silenus, who passed out in his rose garden one night. Silenus so appreciated the monarch's hospitality that he offered Midas a reward. Midas asked that whatever he touched transform into gold, a delight that soon cost him his daughter when he hugged her, and almost cost him his life, since for a time even food turned into gold when it touched his lips. Obviously, none of that probably ever happened to the real king, but there's evidence that Midas earned his legendary status for good reason. It all traces back to the Bronze Age, which began in Midas's neighborhood around 3000 BC. Making bronze, an alloy of tin and copper, was the high-tech field of the day. But in saying bronze, we need to be more specific. It's not like water, in which 2 parts hydrogen always combine with 1 part oxygen. Many different mixtures with many different ratios of metals all count as bronze, and around the ancient world, bronze metals varied in color, depending on the different percentages of tin, copper, and other elements that were present. One unique feature of the metal mines near Phrygia was that they contained many ores with zinc. Zinc and tin are commonly found together in nature, and it is easy to mistake one metal for the other. What's interesting is that zinc mixed with copper doesn't form bronze, it forms brass, and the earliest known brass foundries were found where Midas once reigned. Is it obvious yet? Go find something bronze and then something brass and examine them. The bronze is shiny but with a reddish copper color. You wouldn't mistake it for anything else. The color of brass is much more golden. Midas's touch was possibly nothing more than an accidental touch of zinc in the soil of his kingdom. Greek travelers probably loved the Phrygian bronzes because they were so much brighter than their own. The tales they sent home might have grown, century by century, until golden-colored brass became real gold, and Midas's legendary superpower to create precious metals at a touch became the story, a myth with a believable origin. Counterfeit currency. Midas's zinc is a case of unintentional deception, an innocent moment in history that is surrounded by many other examples of deliberate counterfeiting. A century after Midas, the first real money appeared in Asia, coins made of a natural silver-gold alloy called electrum. Then another fabulously wealthy ancient ruler, King Croesus, figured out how to separate electrum into silver and gold coins, and in the process established a real currency system. Just a few years later, in 540 BC, King Polycrates on the Greek Isle of Samos began buying off his enemies in Sparta with worthless lead that had been plated on the outside with gold. Ever since then, counterfeiters have used elements such as lead, copper, tin, and iron to make the real money stretch a little further. If the chemistry of metal coins once favored the cheats, in the age of paper money, the unique chemistry of metals such as europium, element 63, helps government prevent counterfeiting. It all traces back to the chemistry of europium, and especially the movement of electrons within its atoms. So far, we've discussed only the movement of electrons between atoms, but electrons constantly whirl around their own nuclei too, a lot like planets circling a sun. But electrons cannot take just any old path around a nucleus. They move in a very specific path, each having its own specific energy. There's no energy level between the first path and the second path, nor is there any energy level between the second path and the third path, and so on. That means electrons are allowed to orbit only at certain, very specific distances from their sun. They whiz around in weird shapes and at funny angles, but always at fixed distances from the nucleus. However, if an electron is given a burst of energy by heat or the shining of light, then it can jump from a low energy path to an empty, higher energy path. Unfortunately, the electron cannot stay in the high energy state for long and soon crashes back down. As the electron crashes down, it releases the energy that it gained when it jumped up by giving out light. The color of the light that the electron releases depends on the relative energies of the starting and ending levels. A crash between closely spaced levels releases low energy reddish light, while a crash between more widely spaced levels releases high energy violet light. The light given off by electrons in atoms in this way is always made up of very specific, very pure colors. Each element's shells sit at different energies, so each element releases its own characteristic bands of color that are unique to it, the very bands Robert Bunsen observed with his burner and spectroscope. Europium can give out light as described above, but not very well. Europium and other lanthanides can emit light in a different way called fluorescence. Fluorescence involves whole molecules rather than just electrons. Fluorescent molecules absorb high energy light, ultraviolet light, but emit that energy at lower energy visible light. Depending on the molecule it's attached to, europium can emit red, green, or blue light. The European Union, EU, uses europium in the ink on its paper bills, a nice coincidence. To prepare the ink, EU Treasury chemists put europium ions in the fluorescing dye. The europium appears dull under visible light, and a counterfeiter may think he has a perfect replica. But beneath a special laser, the sketch of Europe glows green. Stars become yellow or red, and monuments and signatures and hidden seals shine royal blue. Officials can spot counterfeits simply by looking for bills that don't show all these signs. There are really 2 euros on each banknote, then. The one we see day to day, and a second hidden euro mapped directly onto the first, an embedded code. This effect is extremely hard to fake without professional training. The europium dyes make the euro the most sophisticated piece of currency ever devised. Europium, dyed banknotes, certainly haven't stopped counterfeiting. That's probably impossible as long as people like holding cash. But in the periodic table-wide struggle to slow it down, europium has taken a place among the most precious metals. From precious to productive. Ounce by ounce, the most valuable element among the elements you can actually buy is rhodium, element 45. That's why, to trump a mere platinum record, the Guinness Book of Records gave former Beatle Paul McCartney a disc made of rhodium in 1979 to celebrate his becoming the best-selling musician of all time. But no one ever made more money more quickly with an element on the periodic table than the American chemist Charles Hall did with aluminum, element 13. Because of its shininess, aluminum was once classified as a precious metal, like silver or platinum, element 78, worth hundreds of dollars an ounce. In the mid-1800s, a Frenchman figured out how to extract the metal for industry, making aluminum available commercially, for a price. It was still more expensive than gold. That's because, despite being the most common metal in the Earth's crust, around 8% of it by weight, hundreds of millions of times more common than gold, aluminum never appears in its pure form. It's always bonded to something else, usually oxygen. Pure samples were considered miracles. The French once displayed aluminum bars next to their crown jewels, and Emperor Napoleon III reserved a prize set of aluminum cutlery for special guests at banquets. Less favored guests use gold knives and forks. In the United States, government engineers, to show off their country's industrial achievements, capped the Washington Monument with a 6-pound pyramid of aluminum in 1884. Aluminum's 60-year reign as the world's most precious metal was glorious, but soon an American chemist ruined everything. The metal's properties, light, strong, attractive, and the fact that there is so much of it in the Earth's crust had people pretty excited, but no one could figure out an easy way to separate it from oxygen. That was until a student at Oberlin College in Ohio named Charles Hall solved the problem. Hall worked on separating aluminum throughout his undergraduate years at Oberlin. He failed and failed and failed again, but failed a little more smartly each time. Finally, in 1886, Hall ran an electric current from handmade batteries, power lines didn't exist, through a liquid with dissolved aluminum compounds. The energy from the current separated the pure metal from the oxygen, which collected as tiny silver-colored nuggets on the bottom of the tank. The process was cheap and easy, and it would work just as well in huge vats as it had on the lab bench. This had been the most sought-after chemical prize for years, and Hall had found it. The aluminum boy wonder was just 23. Hall's fortune was not made instantly. Another chemist, Paul Héroult in France, stumbled on more or less the same process at the same time. Today, Hall and Héroult share credit for the discovery. An Austrian invented another separation method in 1887, and with the competition heating up, Hall quickly founded what became the Aluminum Company of America, or Alcoa, in Pittsburgh. It turned into one of the most successful business ventures in history. Aluminum production at Alcoa grew incredibly quickly. In its first months in 1888, Alcoa made 50 pounds of aluminum per day. 2 decades later, it produced 88,000 pounds per day to meet the demand. And while production went up, prices went down dramatically. Years before Hall was born, one man's breakthrough had dropped aluminum from $5.50 per pound to $18 per pound in 7 years. 50 years later, Hall's company drove down the price to 25 cents per pound. At his death in 1914, Hall owned Alcoa shares worth $30 million, around $650 million today. And thanks to Hall, aluminum became the utterly super common metal we all know today, the basis for pop cans and pinging Little League bats and airplane bodies. I suppose it depends on your taste whether you think aluminum was better off as the world's most precious or most productive metal. Incidentally, throughout this book, I use the international spelling of aluminum instead of the strictly American aluminum. Aluminium instead of the strictly American aluminum. This spelling disagreement traces its roots back to the early 1800s. The original spelling matched the ium of the recently discovered barium, magnesium, sodium, and strontium, element 38. When Charles Hall applied for patents on his electric current process, he used the extra I too. However, when advertising his shiny metal, Hall was looser with his language. There's debate about whether cutting the I was intentional or simply a mistake on the advertisements, but when Hall saw aluminum, he thought it was brilliant, and since it aligned his product with the very classy platinum. His new metal caught on so quickly and grew so economically important that aluminum became the American spelling. As always in the United States, money talks.